Okay, so let's go ahead and get through all this stuff today. We're probably won't finish it completely, but that's okay. Whatever we get done with today will be the cutoff for the exam, and then you'll see the practice assignment, not the practice assignment, but the actual assignment. It'll be posted after class today, and then the quiz will be posted after class. Just remember that the assignment is not due till Monday, even though we have an exam on Monday, and then the quiz will not be due until Friday night. Okay. All right. So in continuation of the chemical elements, right? And you'll start to see that a lot of the things that we're going to be doing in this particular unit, we'll jump into a lot of chemistry next unit after this exam, but a lot of what we're doing now is going to be about trends, okay? About trends in the periodic table and such, okay? So let's talk about the occurrence of elements, right? In the human body, it's like 65% oxygen and 18% carbon, right? That's interesting because in the Earth's crust, it's 47% oxygen and 27% silicone, right? It's acting weird. It's acting weird. Like it's shaky or something. Oh well. Does it bother you? Should I fix that? Yeah, it doesn't bother you. No one's talking, so it's fine. And then, so interestingly enough, right? Um, you might think that this is super different right here, where you see, the human body is 65% oxygen and 18% carbon, and Earth's crust is 47 oxygen. And then, I mean, why doesn't it have any carbon in it? Interestingly enough, though, if you look at the periodic table, carbon and silicon are actually in the same group up here on the periodic table. I'm pointing at the wall over here, and um, and so when you see that an element is actually in the same group or the same family on the periodic table, they have the same properties. Okay, they have the same properties. So it's not so dissimilar to have oxygen on, carbon here in the human body and silicon here in the Earth's crust. So analyses of electromagnetic radiation from space indicates that the universe consists of. Um, so the way they did this is with those emission line spectra we did from last chapter, right? They found that the most of the universe consists of hydrogen at 75%, helium at 24%, and then 1% others. So the vast majority of the universe is what? Hydrogen and helium, right? Hydrogen and helium. And the funny thing, or the interesting thing about that, is that everything else kind of stems in the universe stems from those two elements, right? They collide with each other and they become more bigger elements, and then eventually you get the 116 or however elements we have now on the product table. So Earth's atmosphere here is 78% nitrogen and 21% oxygen, and it's about 1% argon, right? So I think I told you guys this before, but back in the day, there used to be a whole lot more oxygen in the atmosphere, right? And uh, and back then, this was like during the Carboniferous period of the Carboniferous period, where we had these really big insects like huge dragonflies, you know. And the reason why we had those is because insects, if you didn't know this, don't breathe the same way we do. We breathe in with our lungs, and we breathe in oxygen, and it gets diffused into our blood, and it goes throughout our bloodstream and stuff like that. That's not what happens in insects. Insects actually have holes in their exoskeleton, and the holes are there so that oxygen can go into those holes, right, and then go to the rest of the body of the insect, right? So they don't have blood transporting oxygen like we do. And so, interestingly, at 21% oxygen, right? That's just not enough oxygen, right? Not a very efficient amount of oxygen for insects to consume that oxygen and to become very big, right? But back then during the Carboniferous period, it was like, I think it was like almost like 40% oxygen, right? And back when it was 40% oxygen, insects got really big because there was a whole bunch of oxygen being pumped into their little holes where they breathe, right? And so that's why they got so big. But the other dangerous thing here too is that with so much oxygen in the atmosphere was very reactive. It exploded. Well, you could get a fire super easy with that much oxygen. So it was a good thing there wasn't any man around at the time, right? Just big insects, unless they had like fire sticks or something. Those insects, okay. So, and then we have the Earth's core, 85% iron and 15% nickel, right? Uh, we used to remember that this is where the magnetic field comes from in the Earth, but the problem with that is that both these metals are heated all the way up to the Curie point, so they can't have any ferromagnetic properties, and so we're like, huh, I wonder how we have molten iron and nickel under the Earth's crust and still have at its far beyond its Curie temperature and still have magnetic lines for compasses to work and such. So that's still a mystery. It's definitely still a mystery. So let's take a look at this little pie graph here that shows the abundance, the relative abundance by mass of elements in the Earth's crust, right? So there's a whole bunch of oxygen inside the Earth's crust. And then the next thing is silicon, which we saw already in that previous statement, right? Uh, so that's 74% of the Earth's crust is actually composed of oxygen and silicon, right? But then we have all these other things too, like 82 other elements is this little guy right here, that little tiny little guy, 2%. Magnesium, 2%. Potassium, 2.5%. Sodium is 3%. Calcium is 3.5%. Iron is 5%. Aluminum is 8%, right? So it's interesting that when we see the world around us, most of it is like solid stuff, right? You know, walls and floors and desks and stuff like that. Uh, but the vast majority of the elements in the Earth's crust is what? It's a gas, right? It's kind of crazy that way. So let's talk about atoms again, just real quickly, because we were talking about atomic physics before, right? The individual units, the atoms, are packed in a repeating pattern, okay? But noble gases occur as single atoms, whereas things like hydrogen atoms are diatomic, okay? So here's iron, and we talked about this before when we were talking about the thermal expansion of metals, right? Where metals have this crystalline structure, right? Where they're arranged very tightly packed with each other in a very organized way, right? And so they have this very organized structure. And then electrons are floating around these metal atoms, right? In this thing we call the electronic sea, right? We call that the electronic sea, okay? But then you get to a gas like neon, right? You get to a gas like neon, and neon is individual atoms of neon just bouncing around, right? So that's a single atomic or a single atom element, right? And then we have hydrogen here, which we call a diatomic because it can only exist like in gaseous form, bouncing around like that. It can only exist as a diatomic molecule where it has two hydrogens together. So we call those diatomic. Okay, and there are a few diatomics that we know of. For example, if you look at the periodic table, oxygen is a diatomic. You always see oxygen as O2. You always see as nitrogen as N2. You always see fluorine as N2. You always see chlorine as Cl2, bromine as Cl2. So all those are diatomics. They all have two of them together. And then the noble gases, right, that start with helium all the way down to xenon here, are all individual, right? They're all single atoms like neon is. And then all these guys in the middle here, the metals, they're all in that packed very close together, right? Very organized way type of thing. This is why they can be magnetic, by the way, because they're packed so neatly, right, in this little shape, this little crystal surrounded by an electron sea. Okay. So your first question for today is this: which of the following is true about atoms? They are individual units packed in a repeating pattern. That seems reasonable. Noble gases occur in a single atom. That seems reasonable too. Some occur as diatomics, or is all these statements true? I wonder if my other class is still over there, or if they've left already. The class is over. If they still need to get work done, then they still need to get work done. And it's not my fault, okay? I did not give them like so much work to do that they had to stay late or something. The lab is supposed to end at like 4:45, and the vast majority of the people in that class got done like in an hour, or two. So they left at like 3:30. So there were just a few stragglers. No, I don't want Firefox. What would I do that for? While you guys are answering this question, the craziest thing happened yesterday, right? I was driving down the street, right, and I saw a spider walking across my dashboard, and I was like, "Oh, that's cool. It's not going to do anything." But I take a closer look at it. It turns out it's like a black widow spider. Okay, and I hear black widow spider is super like poisonous. Uh, And I only know it's a Black Widow spider because Black Widow from the MCU has the two red triangles upside down, right? Like looks like an hourglass. This spider had that too. So I freaked out. I was like, oh my God, it's a Black Widow. What am I going to do? And so it climbs onto, I'm still driving, and I'm actually driving down Cooper Street right now. And it climbs onto my little arm that I use to hang my phone, my phone holder thing, right? And I'm like, I got it. So I'm driving. I take my phone off the holder thing, and I roll down my window, and I'm driving. And while he's sitting there on the thing, I grab my phone holder thing, rip it off the dashboard, and just throw it out the window. The whole thing. So, so Marla, my girlfriend, was riding with me yesterday, at night, because we went to go get like Wingstop at really late at night. By the way, did you know that they give you free food at Wingstop if you get there right before they close? Yeah, yeah. Look, because they close at 11. We got there at like 10:55, and we ordered like an all-in bundle, and so they're like, okay, give us 5 minutes, and so I went back into the car to wait, and I came back inside, and it was like I had my card out, and they're like, oh, don't worry about it, we've already shut down all the registers, you can just have it. I'm like, thanks. So I'm not saying you should do that all the time because they might start, catching on, but maybe once a quarter, go to Wingstop right before they close, once every 3 months. Um, but anyway, so that was really nice of them. But yeah, so she was like, "What happened to your phone holder?" I'm like, "Oh, there was a Black Widow spider. I had to get rid of it." She's like, "Oh, she was the whole phone holder." I'm like, "Yeah, it made its home in the phone holder. I didn't want to, get bitten." So the funny thing about that is that she really hates spiders too, like all spiders, not just Black Widow spiders, all spiders. And she told me the story about how she was driving one time and there was a spider on her dash, and she actually negotiated with it. She wasn't as aggressive as I was, and she negotiated and she said, "Okay, spider, if you stay right there, don't move at all, I won't crash the car and kill us both." And so it stayed there the whole time. And then she got home, and I didn't know that's what happened, right? But she told me to come outside, and I killed the spider for her on the dash. So, so I guess negotiation works well too, and you won't lose a phone holder. I could go back. It was an empty. I told this. I told my other class this story too, and they're like, "What if you hit somebody? You like, what if it?" And I'm like, "Well, I mean, it threw it into a field, so maybe I should go back and see if my phone holder's still there." It probably isn't. So I don't know. I forgot to look up how you answered this question, but make sure you all signed in. So for attendance purposes, of course. But the answer here is all the above is true. Okay. The answer here is all the above is true. So we switch over from talking about atoms to talking about molecules, right? So molecules are electrically neutral particles that are composed of two or more atoms, right? That are chemically combined. Okay. That's what the difference is between an atom and a molecule. An atom is a single unit of an element, right? Like a single unit of boron or a single unit of neon, right? Whereas a molecule, right, is two or more atoms chemically combined with each other, right? So if the atoms are the same of the same, sorry about that. If the atoms are of the same element, then the molecule is of an element. For example, these are those diatomics I was talking about before. Hydrogen is an H2, nitrogen is an N2, oxygen is also O2. Um, and then all the ones in the halogens, fluorine, chlorine, bromine, iodine, all those are all diatomics, right? But then, if atoms have different elements in it, then the molecule is of a compound, right? So compounds are examples here with water, and then we have ammonia here, which is what you use to clean your windows with. But if you ever has anyone ever seen the movie Boondock Saints before? There's a part in Boondock Saints when William Dafoe is at a crime scene, and there's like blood spatter on this doorway because they just got shot up by El Duce or something like that, right? The guy's name is El Duce, and and there's all this blood, right? But he wants to collect the blood. He wants to collect the blood for like analysis, but they can't for some reason collect the blood until he touches it with his bare hand and he smells it. And he's like, "Oh my God, there's ammonia here!" Right? And he's implying that the ammonia has somehow destroyed the blood, right? And he can't get samples from it. I just want to say that I have never heard of that ever in my entire life. and I've been a forensic scientist for multiple years, so I have no idea what William Dafoe is talking about there, right? But the one thing that is correct about what he said is, or what he did, was that when you smell it, it's pretty strong, right? The smell of ammonia is pretty strong. So that's definitely a compound right there. So when I ask you about ammonia on the exam, just think about William Dafoe, trying to, and he's like, that's ammonia, right? He's so adamant about it. If you haven't seen Boondock Saints, I highly recommend it. It's a fun movie. Seriously, no one's seen this except for Cameron? Like, no one's seen Boondock Saints except for Cameron. They're coming out with like a Boondock Saints 3. So it's a good movie. It's a really fun movie. It's a very fun movie. Okay, moving on to something that's more relevant, right, to you guys. I don't know if it is or not, right? We can actually see molecules in these different shapes. For example, we have hydrogen here, right? Two hydrogens bonded together with one bond right there, a single bond, and that's H2. We have water here, right? H2O, and that's what it looks like. So we call this the ball and stick model right here, and we call this the space filling model, okay? So you can see how this molecule here is, for example, linear. This one is bent, right? And here we have here ammonia. Ammonia, with its ball and stick model and its space filling model, is what we call a trigonal pyramid, because it kind of looks like a pyramid, right? With three sides. So we call it a trigonal pyramid. And then we have here a methane molecule, right? Methane. And methane is a carbon with four hydrogens around it, right? And while that may look like a trigonal pyramid to you, it is in fact a structure that we call a tetrahedral, right? Which is a four-sided three-dimensional structure, right? A tetrahedral. Only thing is it's not a cube, right? It's kind of like a diamond, right? A three-dimensional diamond. So it's called a tetrahedral. So, for example, you've heard the phrase hedron before. For example, there's the dodecahedron, which is a 20-sided three-dimensional molecule, three-dimensional shape. There's the icosahedron. There's a whole bunch of them. Okay, so after a while, you just don't have special names for them anymore. You just call them by the Greek number, and then you add the word hedron at the end, right? All right. So there are 7 common elements that exist as diatomics. Oh my gosh, I just said that a second ago, and now there's a picture. How convenient, right? These atoms are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, right? They are too reactive to exist as independent atoms, so that's why they're diatomics, right? And then when you write their formulas with 7 elements, when writing the formulas with these 7 elements, we use a diatomic form, right? So for example, here we have hydrogen, and we add it to chlorine, and then we get 2 hydrochloric acids, okay? And so here's a nice little picture that shows you the diatomics from the periodic table, right? We have hydrogen there. We have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These guys all exist as diatomics. And I'll show you a video next week or something when we get more into chemical reactions. But like chlorine is super insidious. Okay, chlorine, if it's not with itself, because it's kind of incestuous that way, it likes to be with itself. If it's not with itself, it will break bonds to rip electrons from things. Like literally, it will literally rip off electrons from other atoms like they're little kittens. Like chlorine is that mean. And the example of this is the fact that back during World War One, Haber used the chlorine atom, right, or chlorine gas as a bioweapon against Allied forces, right? He'd throw a bomb out there that was all chlorine gas, which is really bad, right? Because the chlorine gas would get inhaled by the troops, and when it was inhaled by the troops, it would turn into hydrochloric acid. How did it do that? It did that because these, like I said, chlorine atoms, they're insidious, and they'll take electrons from like babies and kittens, right? And so it would rip an electron along with a hydrogen from the water that's in your lungs and in your throat, right? And when it does that, it becomes hydrochloric acid. And then now your throats are burning from acid burning, right? Because of the chlorine atom, right? So chlorine is super, super insidious, right? Super dangerous. Which is interesting because if you add chlorine right here, which is super dangerous, right? and you add it to like something like sodium, which is also explosive, right? It becomes salt, table salt. It's something we all use all the time, right? Unless you have high blood pressure, which I don't have high blood pressure, but I'm just being inclusive for trying to be more inclusive of people that have high blood pressure. I don't know why. Why would I do that? That's so dumb. Are people with high blood pressure feeling like they're not being included in things? I have no idea why I even said that. I'll cut that out from the video. Sorry. Anyway, we'll watch a video about that later though. Okay, so no, not about high blood pressure people, but about sodium chloride is what I'm saying. Okay, so then there's these things called allotropes. Okay, two or more forms of the same element that have different bonding structures in the same physical phase. For example, diamonds and graphite, right, are all they're all made of carbon, right? Diamonds are made of carbon. So have you ever watched? Was it the original Superman where he like took some charcoal and he squished it in his hand and it became diamonds? Right? I think that was the original Superman movie. Um, Obviously, making diamonds takes like hundreds of thousands of years and a lot of like earth pressure and stuff. It can't just be done by a Kryptonian, right? But it's still made of carbon, right? Which is interesting because charcoal is also made of carbon, and the graphite that's in your pencils is also made of carbon, right? But they're so different when it comes to what they look like in their physical states, even though they're all made of carbon. So those are what allotropes are. Okay, both pure diamond and pure graphite are each 100% carbon, and both are solid. But the atomic arrangement of the atoms is what is different. So let's take a quick look and see why it's different. So here's diamond, right? Here's a diamond, and you see that it makes this very simple shape right here. I don't even know how many sides that is, right? But you see that there's a diamond, and that's a shape that uh, the shape that the carbons are arranged in. Okay, but then we look at the graphite that's in your pencils. Okay, if anyone still uses a pencil, right? This is what it looks like, where all the carbons are in these six-membered rings, right? And then they're weakly bonding to each other, attracted to each other in the perpendicular direction, right? And then we have another thing here. This is called a fullerene. Specifically, it's called a buckyball. Um, it's not called a buckyball because Bucky Barnes. It's called a buckyball because another guy that discovered it, Buckminster ball. I can't remember whatever it is. Some guy named Buckmeister. I can't remember. Anyway, it's a 60-sided, 60 carbon molecule, right? 60 carbons making this big ball right here. You can actually go to like cool little science shops online and buy these things called Bucky balls, right? And they literally they're like magnetic balls, and you throw them together and they form one big ball. It's really fun. I don't know if you ever tried it before, but it's really fun. Anyway, which of the following which of the following is not an allotrope of carbon? Diamond, graphite, malachite, or buckyball? This should be pretty obvious because one of them is absolutely made up. So the vast majority of you guys all picked C, and C is indeed correct. I totally made up malachite, and I made up malachite because it rhymes with graphite. So that's totally a made up word. So good call, good call. All right, so we have some allotropes of oxygen too, where we have oxygen, which is the gas that we all inhale, and then CO2, what we all exhale, much to the dismay of the FedEx employee that didn't believe me when I told her that, right? But we do exhale carbon dioxide. That has nothing to do with this. It's not an allotrope. But oxygen does have two allotropes: the oxygen molecule that we all inhale, and then we also have the ozone molecule, right? That's in the atmosphere, right? O3. Okay. Um, hmm. I was going to say something about ozone. I can't remember what it is now. Oh well. Moving on. Okay. The periodic table. Okay, so now we're going to start talking about some of the trends of the periodic table, which a lot of the exam, right, will be not a lot of the exam, but some of the exam will be trying to identify different periodic trends. Okay, for example, I give you three atoms, and you have to tell me which is the largest atom, right? or I give you three atoms, and you have to tell me which is the most electronegative atom. You're going to learn all that right now, right? So it won't be that hard, I promise. Okay. So, and then you'll also have the cheat sheet known as the periodic table on the board here for you to be able to use during the exam. I mean, I could take it down, make you memorize it. Yeah. Well, yeah. I'm kidding. I am not going to exert that much energy to pull down that thing and then have to put it back up. No, I could make you guys do it. Just kidding. Kidding. Okay, so the periodic table puts elements in order of increasing atomic number into 7 horizontal rows called periods, right? So these are here, like when you go downwards right here. So this is period 1, 2, 3, 4, 5, 6, 7, right? So the horizontal rows are called periods, okay? The periods of elements are the periodic functions of their atomic numbers. And so this guy, I think I talked about him before, in 1869, Mendeleev published the original periodic table. God, and he was so smart that there was already elements that he had discovered, and he actually left gaps in the periodic table back in the late 1800s, left gaps in the periodic table so that other elements could be found, and they were inserted in those gaps, and they fit perfectly with Mendeleev's first periodic table back in the 1800s, which is crazy. I can't even predict what I'm going to have for dinner, and he predicted like 80 elements or something, right? Anyway, wait, that's not right. Whatever it said in the last few slides about him predicting elements. Can't remember how many he found. Anyway, so we have rows, and those are called periods. There's 7 of those. And then the other thing we have is called the columns, right? They're called groups. There are 15. There are 15 groups, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the vertical ones, the vertical are groups, right? There are 15 of those. And then the horizontals are called periods, and there are 7 of those. Okay? So let's first talk about this. Oh, I could have just shown you this picture a second ago, right? So here are the representative elements. I don't really know what that means, but the green here, these are all elements that are pretty much what they are, what they say they are. So the first group here is called the alkali metals. The second group here is called the alkali earth metals. Okay? And those guys are important because they make a lot of our ionic compounds like sodium chloride, which is salt, calcium carbonate, magnesium sulfate. All these different compounds that we use in life today are made with the metals that are in the alkali earths and the alkali metals. Okay? And then on the right-hand side, we have, of course, our noble gases, and we have our halogens. So the reason why they're called noble gases is because these noble gases only like to be with each other. Okay, like helium, not be with each other, but be with themselves. Right? Helium is not gonna ever combine with anything on the rest of the product table. Neon won't do it either. Argon won't do it either. Krypton won't do it. Xenon, radon, none of those will do it. Right? They will all stay all by themselves here in this row 8 because they're the noble gases, and I'll tell you why in a second. The halogens, though, the halogens are quite reactive, right? They're so reactive, that's why they always have to be in the form of a diatomic molecule, right? Like chlorine, which is Cl2. And if it weren't Cl2, or even if it is Cl2 and it gets into your throat, it's going to rip off a hydrogen and an electron from your water in your throat and burn out your esophagus. Wait, not your esophagus, you equal your esophagus. Burn out your trachea, right? It's crazy stuff, that chlorine, right? So when we talk about like a lot of what we call ionic reactions that make salts like sodium chloride, magnesium sulfide, all those guys, they're always going to be with the metals over here, the alkali metals, the alkali earth metals, and then the halogens, very, very commonly. Okay? And then I may have told you last time too that there's also these things called the lanthanides and the actinides, also known as the F block elements. Yeah, nobody cares about those. I mean, some people care, but I don't care about those. All right, so this is just the same slide again. Just showing you these are the transition elements here, the representative elements here, and yeah, it's the same slide again. All right, so here's another periodic trend to talk about, right? All these guys over here, right, are called nonmetals, with the exception of hydrogen being over here, also nonmetal, right? But everything else on the periodic table in this blue color are metals, okay? So the periodic trend that you need to notice here is that metallic character decreases as you go to the right of the periodic table, but non-metallic character increases as you go to the right of the periodic table. And then when you go down the periodic table, metallic character increases, and then non-metallic character decreases. Okay? So one of the kind of examples, one of the kind of questions I might ask you on the exam is, I might give you like 3 elements, right? And using this logic, the more to the right or down to the more to the right or more down it is, right? You have to tell me which is more metallic. Does that make sense? Right? Or which is less metallic. Okay? Those are the kind of questions that I might ask you. So remember, in this particular thing, metallic character decreases toward the right, non-metallic character increases towards the right, and then going downwards, metallic character increases, and then also going downward, non-metallic character decreases. Okay? So let's talk about these metals and these non-metal properties. Another thing I might ask you in the exam, which of the following is a property of a non-metal, or which of the following is a property of a metal? Metals, of course, are good conductors of electricity and heat. They're malleable. They can be beaten into thin sheets, right? Ductile, so they can be stretched into wire. They possess metallic luster, so they're shiny, which I don't have anything metallic. Oh, here we go. Like this, see, it's shiny. This is iron right here, and that it's shiny, right? Unless it gets rusty, then it's not so shiny anymore. And then they're solid at room temperatures most of the time. The only one that's not solid at room temperature is mercury, right? I think I may have told you my mercury story before. The time I got contaminated with mercury, that was bad. Um, anyway, don't worry about that. That little guy, don't worry about that little guy. But so another one that has a very interesting melting point too is, have you ever seen the metal gallium before? Yes. Like sitting on the table at like 25 degrees Celsius, it will be a solid, but you can put, you can hold it in your hand, and your hand's warm enough to melt it, and it'll just melt, and it's actually safe, so it's really fun to play with, right? Which I thought mercury was fun to play with too, but apparently it's not. But anyway, gallium apparently is fun to play with and easy and safe, and you can hold it in your hand and it melts. But what the coolest part is that you can take a gallium spoon and like put it into like some coffee and stir it, right? And then it will melt into your coffee. And you're like, what happened to my spoon? What happened? I wonder how that would work on your spoon experiment. Whoever did the spoon experiment, you guys did, yes, right? I mean, how do you test that when the metal's not even there anymore? I should have asked you that question during the presentation. I missed a good opportunity to be like, gotcha, but I didn't. So yes, did you ever have a chance to play with gallium? It's actually kind of fun. There's tons of YouTube videos about gallium, and they'll, like I said, they'll put it into like they'll stir up some coffee, and then they'll take the spoon out, and the spoon's like half gone because the gallium's melted. I don't recommend you drinking gallium. That'd be bad. Okay, that would be bad. All right, so then there is nonmetals. They're poor conductors of electricity and heat. We already knew that. They're very brittle if they're a solid. Non-ductile, which means they can't become wire, right? They do not possess any luster, right? Their solids, liquids, and gases are all at room temperature. So there's for nonmetals at room temperature, they can be solids, liquids, or gases, right? And then so this is the interesting thing, right? Um, Metals have 1 to 3 valence electrons, which we'll talk about in just a second. But nonmetals usually have 4 to 8 valence electrons. Okay. So what a valence electron is the outer shell of an atom has a certain number of electrons. Okay. But every atom wants to get to 8 electrons. Every single atom. Okay. And to get those 8 electrons, like chlorine, they'll rip it away from another atom, right? And so chlorine will rip it away from water and make hydrochloric acid in your throat, and then it'll have 8 electrons because chlorine is here in group 17, and that means that it has 7 valence electrons. It just needs one more to get to 8, right? And that's why it's so insidious. So that's why it's so violent when it comes to ripping electrons away from kittens, right? But notice here though that group 18, the noble gases, they have 8 electrons in their valence shell on the outer shell, right? That's why they don't want to, associate with anybody else. They don't need to. They've got 8 electrons. They're happy the way they are. So they don't need to go ripping electrons away from kittens, right? So all the nonmetals, right, have either 8 electrons on this on noble gases, which they don't want to interact with anybody, or they have 7 valence electrons in the halogens, right? And so the halogens will rip off electrons from kittens, right? What if in the test I had a picture of a kitten getting like something stolen from a kitten? Would you know what that was in reference to, right? And good, that's what I'll do. I'll make a little GIF or something of a kitten like someone stealing a lollipop from a kitten or something. Why would a kitten be holding a lollipop? I don't know. What? But then the lollipop could be like the electron, right? It's being stolen away from the kitten. Get it? Get it? Okay. Oh, good, good. Anyway, so 1 electron missing from halogens. That's why it wants that 1 electron, right? Oxygen's group has 2 electrons missing. Nitrogen has 3 electrons. Carbon has 4 electrons missing, right? So that's what a valence electron is. And then they lose electrons to form positive ions, and they gain for metals, and then non-metals gain electrons to form negative ions or to share electrons. And we'll talk about that in detail in just a second. I need to take a sip. I'm getting parched. All right, so let's talk about this in very more detail right here, okay? So like I was saying before, so electrons are in different energy levels that we were talking about in the atomic physics section, right? And so at level 1, right, or at n equals 1, the maximum number of electrons is 2. At n equals 2, or level 2, the maximum number is 18 electrons, or sorry, 8 electrons. At level 3, it's 18 electrons, right? And so the chemical reactivity of elements depends on the order of electrons in these energy levels, okay? In these energy levels. And so the thing is, right, not most, but all atoms want to get a full outer shell. So for ones that only have 1 or 2 electrons, 2 is what they want to get to, right? So hydrogen wants to get an electron too, okay? For the vast majority of all the other elements, they're all trying to get to 8 electrons, okay? They're all trying to get to 8 electrons. You don't have like 18 electrons till you get down to these big guys down here, but we don't really talk about the big guys at the bottom, okay? So, I just said that we only discussed the representative elements groups 1A through 8A. Okay, so this is the same thing again, and it's all it's really showing you is the fact that we're talking about these guys here, right, and these guys here. The non-metals over here and these metals here, and they will combine with each other to try to get 8 electrons, except for the noble gases, which already have 8 electrons in their outer shell, so they don't really care about anybody else. Okay. So the outer shell. So these are the facts that you need to know about valence electrons right here. The outer shell of electron atom is known as the valence shell. The electrons in the outer shell are called the valence electrons, right? So the shell is called the valence shell, and then the electrons that are in that shell are called what? Valence electrons, okay? Valence electrons are involved in chemical bonds, so they're extremely important, right? And so elements in a given group will have the same number of valence electrons, okay? Or similar chemical properties, which I told you that already before when I said that oxygen and silicon were in the same group. So they're not so dissimilar. And the reason why they're not so dissimilar is because carbon and silicon. Carbon and silicon are in the same group, so they're not so dissimilar from the Earth's crust and from the human body, right? And the reason why they're not so dissimilar is because they both have 4 valence electrons. Does that make sense? 4 valence electrons, okay? And then of course nitrogen and phosphorus, they're in the same group, so they all have three valence that they need to get rid of. Not get rid of. Yes, they need 3 valence electrons, right? And then um, um, oxygen has 2, right? And then I'm saying that backwards. I apologize. So carbon has 4, definitely, that's correct. Nitrogen and phosphorus have 5 valence electrons. Oxygen, sulfur have 6 electrons, and then fluorine's group, which is the halogens, chlorine, bromine, and iodine have 7 electrons, and then the noble gases have 8, right? So what I was telling you before is how many electrons they need to get to 8. right? So if carbon has 4 valence electrons, how many does it need to get to 8? 4 electrons, right? And then nitrogen has 5 valence electrons. How many does it need to get to 8? 3 electrons, right? And then oxygen has 6 valence electrons. How much does it need to get to 8? 2, right? And then fluorine has 7 valence electrons. How many does it need to get to 8? 1. Okay? So that's what you need to know about that. Okay? So here we go. Which of the following is not true about valence electrons? The electrons in the inner shell are called valence electrons. That seems questionable. The valence electrons are the electrons involved in forming chemical bonds. That's kind of questionable too. Elements in a given group all have the same number of valence electrons. I don't know if that's true or not. And then all of these are true. I see you don't ever have any problems anymore, Carly, with your phone. Oh, did I change that or something? Oh, you know what it is too? I used to have it completely stretched out. And maybe that made the brightness a little bit darker. But then I changed it to have a 16 by 9 aspect ratio. Oh, I need to pay attention to this. Only 10 people have responded so far. So now I got to go home and boil that freaking Wonder Packs thing to get it back to normal again. Caitlin, can you grab it and bring it up here? Or leave it up here? So I can put it back in its box? Is it still hot? Really? This stuff stays hot for a very long time. It's already been like 45 minutes. So it's cool stuff though, right? I mean, I wasn't joking. Nothing. It's just sodium acetate. So I mean, you could drink it and it would get very hot inside you. So, but you can see how this kind of thing is like, very, it has like a wow factor. And so when you're at the Home and Garden show and you may be very learned and educated, but then you're like, oh, that's really cool. And then you end up buying like 4 of them and spending almost $500 for no good reason. Well, they had, so this is why they need 4, because they had ones for the back, one for the shoulder, one for your like your lower back, and they had one for your feet. You could, like this one specifically says um, neck and shoulder, right? But there are other ones that say like feet and then lower back, and so we for some reason had to get one for each body part. Yes, whereas you're absolutely right, Sydney. We could have used this freaking one on every body part. So very good point. Just saying, good point. But logic escapes us sometimes. Okay, so in this particular answer here, the answer is indeed A. Good job there, because that definitely says inner shell, and what should that be? Outer shell, right? Outer shell. Good on you guys. Good on you guys. So here we go. Okay. Guidelines for shell configurations. The number of electrons in an atom is the same as the element's atomic number, right? So the thing that everybody gets confused with is valence electrons and then total number of electrons. Okay. So I'll give you an example here. If you look at, for example, oxygen, right? Its atomic number is 8, right? Is it 8? I can't even see it. Does it say 8? Yeah, that does say 8. So its atomic number is 8. So it has 8 total electrons. Does that make sense? But based on the group it's in, right, all you have to do is drop the 1 from the group number, right? And it has 6 valence electrons. Okay, does that make sense? So don't confuse valence electrons with the total number of electrons. The valence electrons is dependent on the group number by dropping the 1 that's in front of the group number. So you drop the 1 and get 6, or drop the 1 and get 4, right? Whatever. So that tells you what the valence is in the entire group. But the number of total electrons is the atomic number. So uh, for um, for carbon, then it would be 6 total electrons, whereas the valence electrons would only be 4. Make sense? So a question I might ask you is, I'll give you, like, say, calcium, right, on the test, and you have to tell me how many, like, for example, valence electrons it has and how many total electrons it has, based on the periodic table. So for calcium, it has how many valence electrons? 2, right? And then how many total electrons? 20. Make sense? Right? It's not going to be too hard, I promise. So the number of shells that contain electrons will be the same number as the period number. So the period number, remember, is the number of the rows, right? And so as the number goes up, that's the number of shells there is. So here at hydrogen, there's only one shell that has 2 electrons. Here there's another shell for n equals 2, right? That has 8 electrons in it too. So the vast majority of the atoms we care about are here that have 8, right? And so as you move up, 1 shell, 2 shell, 3 shell, 4 shells, 5 shells, 6 shells, 7 shells. Make sense? And then for group A of the representative elements, the valence number of electrons is the same as the group number, which I said that already. Okay? So here's an example. Sodium has an atomic number of 11, an atomic mass of, what is U? 23U. What does that mean? It should be AMU, atomic mass units, not just U. So I don't know where this is coming from. I honestly don't know where this is coming from. Give me okay. And so it should be atomic mass units. Okay. So it is a representative element, of course, because it's in group 1A. It's in the third period. So it has 11 electrons, 11 protons, because its atomic number is 11. And then it has 1 valence electron because it's in group 1, right? And then it has 3 shells. And then so the configuration here is 2 electrons in the first shell, 8 electrons in the second shell, 1 electron in the last shell, the third shell, right? And so this 1 electron right here, it's very happy to get rid of in sodium. And so it'll give it over to chlorine, and that's how you get sodium chloride, right? Which is salt. Okay?